Hello and welcome back to the course on blockchain. Today we're talking about distributed peer-to-peer networks. Alright, so previously we've already talked about the hash cryptography, check that one off. We've checked off immutable ledger previously as well. And now we're moving on to distributed P2P networks. So let's have a look. We left off last time when we discussed the example of property ledgers, the traditional approach versus the blockchain approach, and how the blockchain can add more protection and make the whole ledger immutable, make it very difficult for somebody to change previous records in the ledger and therefore make it more reliable. However, the question here is, okay, well, if I'm trying to attack this ledger or if I'm trying to make some change, yes, indeed, previously it was just about ripping out a page or making like a change in a database or an Excel document, which was very simplistic compared to the blockchain approach. But nevertheless, even in the blockchain approach, if this blockchain is maintained just by this government authority, then what prevents me from going in and if I have enough time, then actually changing this block and then changing this block and this and this and this. After all, if we're talking about a property that might be worth a couple $100,000, it might be worthwhile for somebody to actually put in the effort to change the block here, replace your name with their name, and then the hash will be updated, and then they will change this hash and this and this and this and this and so on. So what prevents them from doing it? Or on the other hand, what also happens if, for example, there's some system error, and so, for example, this block is not maliciously changed, but just through somebody's input error or something else, they were going to put in a new block at the end, but by accident they went into this ledger and they just actually changed the value in this block. And indeed, the cryptographic link will be broken, and we'll see that there's a problem, but we'll never be able to restore the previous data, right? It's even though we can see that there's a problem, how will we restore the data? So those are the two questions. On one hand, somebody can come in and actually spend the time to change all the blocks in the system to forge the ledger, even though it will take some time, but it might be worth it for them. On the other hand, something might happen in the middle of the chain, just accidentally, some data might be lost, because at the end of the day, this is just like a blockchain is an open ledger. Anybody can just go in there and see the file, just like an Excel spreadsheet or database. It's there. It's linked like this, so it's harder to change, or we'll see if there's a change. But at the same time, it's not that it is right protected. You can go in and change this, and if that accidentally somehow happens, then how do we restore the data from the original data that's there? And so those are the problems that distributed peer-to-peer networks solve. So let's have a look. So in a distributed P2P system, we've got like lots of computers, and they're all interconnected. Ideally, the more they're connected, the better. But of course, you can't be constantly connected to everybody at the same time. And some like further computers away are going to be connected a bit less to each other and so on. But through the network, everybody is interconnected. And so in this scenario, what we do with the blockchain, how does this affect the blockchain? How can we use this? How is this used in blockchains? Well, the blockchain is actually copied across all of those computers. So let's think about our example of the properties. Instead of just keeping it on one system in that government computer, it's actually copied across thousands and thousands of computers. Here we only have 6 computers in our example, but it can be actually thousands of computers or even millions of computers, just laptops of people or personal computers. Like literally, it could be on your computer, it could be on my computer, that exact government ledger with all the transactions. And of course, it wouldn't have names in it. Everything would be connected through cryptographic keys and things like that, which we'll talk more about in the coming module of the course. So you can't get to the actual names of the people without knowing. It'll be just through their identifiers. But nevertheless, all of this information about all the transactions on everybody's computer, and anybody can on their own computer change this information if they like, or or not change it if they don't want to. Just keep the blockchain being updated on their computer. So that's that's what happens. So that's how the blockchain is distributed. I know it sounds pretty crazy that like a ledger of property transactions would be distributed across peers, like just you and me, just normal people. But nevertheless, let's have a look. Let's go with this example. So once a new block is added, what happens is that information is communicated throughout the network, and that block is added further and further throughout the network until all of the computers have this block. And that might take some time, especially in large networks, but nevertheless, a new block has been added. So in this case, it's the house that we purchased. So we can see it's now copied onto all of the networks. And then what happens is, let's say some time passes, as in our previous example, 3 months or a few years, and more transactions are added to the blockchain in a similar manner. And now the problems come. So somebody tries to hack our entry, or there's like an error that has been made to the entry. Well, let's go with the hacking example, because both of them will have the same solution. So somebody comes along and tries to maliciously attack our entry and take away our house. And so we're going to represent this with a black square. Once they've successfully changed the entry, this is what it looks like. But at the same time, as soon as they do that, we know that the cryptographic links between the blocks will cause a problem for them, because now all of these blocks after that block are all of a sudden invalid, and they need to go through all of them. And as we discussed, maybe it is worthwhile for them to go through all of them and actually change the hashes in those blocks, recalculate the hash of each block one at a time, and re-record them and put the new information in. So they might go ahead and do that. And they're successful, and they've changed this blockchain. So in the previous example, before we had distributed peer-to-peer networks, that would have been the end. They would have succeeded, and they would have taken away that $1 million or $100,000 property. But in distributed peer-to-peer networks, what happens is they're all synced up very constantly. The network is constantly checking. That's how the system is designed. The blockchains are constantly checking their peers to see if their blockchains match up. And so instantly these peers would see that there's a problem, that their blockchain doesn't match up to this blockchain. And they would signal to the blockchain on that computer saying, hey, look, just like computers talking to each other, hey, look, your blockchain seems wrong compared to us. And that blockchain on the right, the blockchain which was hacked, it will notice that it is in the minority, that the majority of blockchains around it are in consensus, like they have the same blockchain, which is different to the one it has. And that means it will understand that it's been hacked. And what will happen automatically is that these values now, where are we? These values, we'll see that these values are different, and these values will be copied over. So just very quickly, all of these values will be copied over, and the blockchain will be just restored to its original value. So what happens in this case is, as we can see, the hacker cannot just attack one computer, cannot just attack one blockchain and change the values there. The hacker would have to attack all of the blockchains and at the same time. So by attacking this one, even if it takes them, like, they would have to do that operation very quickly in a matter of a few seconds, or like maximum a couple of minutes, depending on the blockchain structure. Once they do that, it gets replaced, right? But so even if they're like, if they're taking a while to do it, it'll get fixed even before they get to the end. But now to successfully attack, they actually have to attack, well, not all of the peers. They have to attack more than 50% of the computers at the same time in order to replace to successfully replace the chain. So if they attack, so we got 6 computers, so they'd have to attack 4. If they attack 1, 2, 3, 4 of these computers at the same time and replace these blocks, so recalculate this block and then recalculate the hash for this block and then replace it in all of these computers at the same time, then they could take over the network. That's the only way you can break into a blockchain. And so the more you have computers, the more peers you have in a blockchain, the harder it is. So if you have 10,000 computers, you would have to hack into 5,000 computers, 5,001 computers at the same time and do it within a couple of minutes, and probably a couple of, less than a minute, or depending on the blockchain, yes, a couple of minutes maximum. And that's practically impossible. That's where the additional security comes from. And that also illustrates the point that it doesn't really matter that this blockchain is sitting on my computer. So might be me. The blockchain is sitting on my computer. As long as I can't get any personal details from this blockchain of the people there, as long as they're represented by their identifiers rather than their names and addresses and things like that, as long as it's that's how it's represented, then it doesn't matter, because even if it's sitting on my computer and if I try to accidentally or maliciously change something on this blockchain, then the same scenario will happen. It will just auto-update itself and I'll have the new file. And that's it. And my hands are tied. No one person can do anything. And so that's how we bring trust into a trustless environment. So at the end of the day, if we don't know each other, anybody in this chain, we don't trust each other. But because we have this majority consensus situation, because of that, we can trust each other. The technology setup, the technology design brings trust into this trustless framework and allows us to transact with each other. That's the beauty of distributed peer-to-peer networks in blockchain. And that's, as you can see, that adds an extra level of security. So we had a hash cryptography, that was one level of security. Now we've got the peer-to-peer networks, another level of security. And as we'll see through the consensus protocol and other things, there's more and more layers of security that make blockchains so powerful. So yeah, there we go. Everything's good. Blockchain is back to normal. All right, so I hope you enjoyed today's tutorial. And today I've got some additional reading, very interesting article by Vitalik Buterin, the founder of Ethereum. So we'll learn more about Vitalik in module 3 of the course. But for now, here's a good intro to get acquainted with him. The article is called The Meaning of Decentralization. And you may have heard some debates around the difference between decentralization and decentralized systems and distributed systems. And so Vitalik really puts it all to rest. He shows his understanding of three levels of decentralization. So logical decentralization, political decentralization, architectural decentralization. Very interesting read. I highly recommend checking it out, and also will help you combat any kind of debates you might have with someone where they're saying, no, this is not distributed, this is decentralized, or no, this is not decentralized, this is distributed. And this will give you some additional overview of what's going on there. All right, and on that note, we're going to wrap up. I look forward to seeing you next time. And until then, enjoy blockchains.